like mix it up with something. Yeah. I want to take like couple of one. I want to like roll something. I don't know how you say it. I can like. Is that long?
And you guys are thinking
I really want to go hang. Spoil. Everything that comes to me. I don't mind. But it's like this. Wait, I'm like that. It's like 18 or that. Like I wanted to hear like so nice.
I see there's multiple entities.
Yeah.
Hey, can I ask you like one question?
Yeah.
On this one, which one could be the graph of f? So I said one only.
Yeah.
Because doesn't this imply like it's constant for a little bit before it goes up?
Right. So that is a slope of 0,
Okay.
right? But then immediately to the right of 0, it's already showing positive slope. So it should be. I mean, it was slope 0 to begin with, but then immediately to the right, it's already a positive. Slope.
Okay.
It's like a positive 3, so that should be showing a positive 3, so 2 or 1.
Okay, because I picked one only because I just thought it was immediately going up. So like straight off 0, it's going up. And 3, it's like constant and then up.
Right.
So I was like, I don't know.
Okay, I'll give those points back to you.
Okay, thank you.
Yeah.
It's either really young or. I don't know if it's just either always. I always like that. That's like. I'm like, it's not true. I like to say. Yeah, the Monday. Really? Because we had one last week.
Yes.
And like.
I know it, yeah. No, they just said. You're not taking up skin, right?
I know, I'm.
Yeah, we got that.
It's my.
Yeah.
No one.
Really check.
Easier, someone else.
Then you can translate.
And then we like.
They're already came down, so. Or what are the,
So I did there.
Like you're supposed to be always like.
directed project, not grades?
Or, you know.
Right, option two. Exactly the length. I think that's like.
Like getting your license.
Yeah, but it wasn't direct option.
Okay.
Okay,
Also. It's like, oh, I should be back to the next day. He's like, I hate when I do that to myself, but I feel like he also.
Two actually.
Somehow like without that.
All right, we're on page 39. We'll see how this goes because I would like to cover as much as possible, but I'm also not going to push it if it feels like we're going too fast. So we'll just do as much as we can, and whatever we don't finish between these 2 sections or 3 sections, we'll pick up on Monday after. Okay, so, but yeah, stick with me, but I'm also going to kind of gauge where we are so that I don't want to go too fast and because then that defeats the purpose. All right, so I think we did number 1, or we did example 2, is that right? Okay. So let's talk about example 3. We talked about how if we always want to look to see if we can find a rule initially to work the problem, and usually it's just going to be, power rule. Can we rely on power rule just to expand and work through? But if something looks too complicated for power rule or too messy for power rule, then we look at our second option, which is use substitution. So again, the whole purpose of use substitution is that we're using a temporary variable to create an easier version of the problem, solve that problem, and then bring back the original variable. So the whole point is we're trying to create an easier version of the problem if possible. So if you look at example 3 here, we have x squared, secant squared, 2x cubed. There is no product rule for antiderivatives. So this is all one connected problem. And this is too messy for any one rule to handle. And because we don't have a rule that can handle and we can't merge anything that's given to us, we know our second option is use substitution. And if we're looking for use substitution, we're considering our u value. And the best place to look for the u value is what's inside the parentheses. Okay. I think there's going to be some exceptions, but for now, we're just looking for a set of parentheses to find our u value. Okay. So we see a set of parentheses. We're going to go ahead and underline that 2x cubed and dx because that's our first priority. Our first priority is trying to get this in terms of u and that in terms of du, and then we'll see how things look after that. All right, so we start with our u value. Our u value is 2x cubed. We're always going to do du over dx. In this case, derivative is 6x squared. We go ahead and cross multiply. Oh, 6x squared dx, sorry. Cross multiply and then solve for dx. And then we make our substitutions with the pieces that we underlined, but everything else we're going to keep. Okay. We haven't resolved anything else, so we don't want to make any changes until we see everything in front of us. I replaced the parentheses with u. I replaced the dx with du over 6x squared. Any questions so far? Use substitution only works if you can get all your x's to go away. Okay, so if your x's don't all go away, we can't move forward with our integral process. But in this case, can we get the x's to go away? Yes, yeah, x squared above, x squared below. So that is a good indication that we're on the right track if you can get the x's to disappear. And however, do we have any leftover coefficients that we have to keep track of? Yeah, there's a 6 in the denominator. I'm going to push that out front as 1/6. But then once we get past that 1/6, we should have a rule that matches perfectly with what we want to use. The thing to be aware of with integral rules is that if you don't have a perfect match, then you don't have a rule to use. For instance, if it was like u secant squared u du, there's no rule to match. There's no rule to use. So it needs to look exactly to the letter. Everything needs to be exactly the same if we want to apply the rule. It's okay to push out any coefficients, but once you get past the coefficient, it should be a perfect match. So it's very restrictive with integral rules. We can't create new ones. We can't make adjustments. If it's not a perfect match, we don't have a rule. So we do have a rule for secant squared. We know the derivative of tangent is secant squared. So therefore, integral of secant squared is tangent. So we apply our integral rule with the 1/6 stays. Secant squared becomes tangent of u. And in place, we have a plus c that shows up. Remember that u variable is a temporary variable. So we we went through U substitution to create an easier problem. Once we find the antiderivative, we want to make sure we bring back our original variable x. All right, questions with 3. Okay, number 4, we see a problem that we should always consider. Can I expand my way through and just rely on power rule? Here, we're kind of stuck. Order of operations does not allow us to distribute that x cubed through. So immediately we know that we can't expand, we can't do power rule. We have to rely on something else. So our next option is use substitution. But if we want to go through use substitution, we would like to see a set of parentheses. We don't see a set of parentheses, but we can create one, right? We can turn that radical into a set of parentheses, and that could be a good place to look for our u value. So let's go ahead and rewrite that radical as a parentheses raised to the 1/2. And start making your underlining of the 2 pieces that we are focused on. We're focused on what's inside the parentheses, and we're focused on the dx. That is our first priority. We want to get these in terms of u and du, and then hope that everything else works out. Okay, so our u value. Du over dx. Cross multiply. Okay, and we make our substitutions. So we're just going to substitute what we underlined. Everything else we're going to keep. Replace the parentheses with u. Don't forget there's still a 1/2 sitting there. Dx is replaced with du over negative 4x cubed. Okay, we can't move forward unless all the x's go away, or the x is going to go away for us. Yes. But there is a leftover what in front? Yeah, negative 1/4. Once you get past that coefficient, the integral should show a problem that has a perfect match. We do have a perfect match for that rule. That is just power rule. So now we're going to do our calculus. So power rule, add 1 to the exponent divided by the new exponent. I'm going to flip that fraction up as 2/3. 2/3 times negative 1/4. Becomes negative 2 over 12, or negative 1/6. U to the 3/2, but I know that I'm near the end of the problem, so I want to bring back my original variable. My original variable is x. Any questions? Now you see how all these problems have the x's that cancel out so nicely for us. What is it about our u value that allows our x's to go away so nicely? So look at your u value versus the leftover x. Look at your u value here versus the leftover x. Look at your u value here versus the leftover x. What is it about the relationship that allows there to be a perfect match for the x's to cancel out? Yeah, 1 degree higher. So it doesn't mean that if there's not that relationship that things won't work out. It just means that we have to maybe do more to clean things up. But if you see that match, that degree that is one higher than the leftover, that's a good sign. That means it's an easier problem. We should be able to get things to move smoothly. But it doesn't mean that that if the degrees don't have that relationship that we can't move forward. It just means that we may have to do some additional work. So these are easier problems because of that nice relationship. All the x's cancel out, and you're left with a rule that's available to us, and then we can apply that rule. So, but I want to continue to emphasize that not every parentheses problem is a U substitution. We should always look to see, is it possible to expand? If it's possible to expand, we should apply that. Because if we're doing a problem that's meant for expansion with U substitution is not a catch-all. It can't be used for problems that's meant for expansion. So we always want to explore our first option first before we look at a more complicated option like U substitution. Okay, any questions? Page 39. Okay, page 40. So now we're looking at a problem where it's not so clear as to what the U value is. Well, first off, there is no rule that can handle such a messy problem, right? Tangent to the fifth, secant squared x. And we can't split this up. We can't say, okay, I'll do a rule for tangent, I'll do a rule for secant, and then merge them together. If things are being multiplied, it is one connected thing. We can't split up into individual parts. But what we could do is maybe we can create some parentheses and at least consider some options. So we know that anytime we have this shorthand form for trig, we can always rewrite it with a set of parentheses. Now we see two sets of parentheses, but only one is going to work. Okay. So let's just explore one option to see if we can see a pathway to the end. If our U value is secant, okay, that means we want that tangent fifth to go away. What's the derivative of secant? Secant's derivative is what? Secant tangent, right? That's not a perfect fit because secant tangent is not going to match up perfectly with tangent to the fifth. So if the derivative doesn't live elsewhere in the problem, then we're not going to get things to cancel out nicely. So we know that secant is probably not going to be a good fit for our U value. So let's consider the other option, which is tangent. Okay, if the U value is tangent, what's the derivative of tangent? Secant squared. You see secant squared elsewhere in the problem? Yes, right. There's a secant squared waiting for us. So if you can see a version of the derivative waiting for you, you know that things will pair up when you replace your dx in terms of du, and you're able to kind of look forward to see, you can predict things will work out, things will cancel out. So so we're just exploring our two options before we go too far, and looks like tangent, our U value for tangent is going to be a better fit down the road to get that secant squared to cancel out. Okay, so we let our U value be tangent. Derivative du over dx is secant squared. Cross multiply. Solve for dx. And then we make our substitutions. Replace the first underline with u, replace the dx in terms of du, and we should be able to get things to line up nicely for us. Again, I am only replacing what I've underlined, but everything else I want to keep because I haven't resolved them yet. Remember, you cannot move forward with integral rules unless all the x's go away. And here we see a perfect fit. X's goes away. There is no leftover coefficient, so there's no number to keep track of in front. And now we just have a nice clean power rule to resolve. Okay, u to the fifth becomes u to the 6th over 6 plus c. We're done with the calculus. We just want to make sure we bring back our x variable since u is only a temporary variable. If you leave the 6 below the u, that's fine. I just like to pull the 1/6 out, but it doesn't matter. All right, example 6. Can we expand our way through this problem? Okay, this one we can, okay? We can split this up into individual fractions. We do see a set of parentheses, but again, this is just to emphasize that we should always look to see, can we rely on just expanding our way through? Now, there's nothing here that's too complicated, right? It's not like there's multiple terms in the denominator. It's not like there's exponent outside that's difficult to manage. This is simply an expansion problem. Right, we can split this up into individual fractions. Every term can get its own term, and the only thing we need is power rule. But I just want to keep reminding us that if we try to use substitution, it's not going to work. We should always consider, can I just rely on a simpler rule to get me through the problem? If I can, then that's the appropriate method. So this one we can break up into individual fractions. Bring the y up. And now we just have a simple power rule for individual terms. And here I'm merging the y's together by subtracting exponents. 1 minus 1/2 is 1/2. And all we need to do now is apply the power rule twice. There's no need for use substitution. Flip all the fractions up, multiply by the reciprocal. All right, any questions so far? All right, example 7. This is called change of variable method, but let's just go through the process like we normally would. And then when we hit that roadblock, we'll discuss what are some options. So the first thing we always try to consider is, can I expand my way through? I can't, right? I can't distribute through parentheses raised to the 1/2. So we've considered it. We can't expand. Power rule alone is not going to allow us to get through this problem. Order of operations doesn't allow us to move forward. So we have to consider use substitution. So let's get a set of parentheses to show up. Okay, so what could be our u value? What do you guys think? Yeah, we do see a set of parentheses, so naturally we want to go towards that as our u value. But what's a future roadblock that we're going to experience? Yeah, the degrees are not in a favorable position, right? This will be easier. This is x squared plus 3, because then x squared becomes 2x, and that x will go away. So the x is not going to cancel out on its own. It doesn't mean that we can't move forward. It's just that we may have to do something additional to get the x's to be replaced. But let's just keep going. But we do know that there's going to be a hurdle that we're going to have to resolve there. So u equals x plus 3. du over dx equals 1. Solve for dx, we get du. Make your substitutions. Remember, you're only replacing what you've underlined. You don't want to replace anything else because we haven't figured that part out yet. Okay. Any questions so far? Now, this is what I see some students experience where they see, oh, I have a power rule for x. I got a power rule for u. I'll just apply the power rule individually and then plus c at the end. We cannot do individual parts if I have a multiplication. This is all still one connected. I cannot split them up into individual integral rules. As that'll be a lot easier, but it doesn't quite work that way. So we can't move forward unless this x is replaced. Okay. And we have to basically find a creative way to get that x to go away. Is there something that we can use to replace x in terms of u? We look at something that we've already established. We do have something that connects us between the two variables, right? U equals x plus 3. So if I can get that x in terms of u, then I can move forward. So if I want to do that, what can I do? X is equivalent to what? U minus 3. So there's our ability to work around the fact that initially our u is not going away. Sorry, our x is not going away. So we're making a substitution to get it to the variable that we need. So again, we can't move forward until all of our variables have been down to just u. So replace the x in terms of u. Okay, we're still not quite there yet, but at least we can see a path towards getting ready for power rule, right? This, before we couldn't distribute, but now we can. Now it's u to the 1/2, distribute through the u minus 3. Once I get all these individualized, then I should just be able to apply power rule twice to get to my answer. So distribute the u through. Remember, you're going to add exponents. 1/2 plus 1 is 3/2. So before we were stuck, we couldn't move, but now that we've replaced and expanded, now these are individual terms. They're no longer connected by multiplication. They're separated by plus or minus. These are ready for power rule. These are individual problems. Okay, so replace. Now we're going to go through power rule twice. Add 1 to the exponent divided by the new exponent. Flip the fractions up. Remember, your u is only a temporary variable, so make sure you bring back your x's at the end of the problem. Here, I flip the 2/3, 3/2 up, that's 2/3. 2/3 times 3 is just going to be 2. And I'm just going to save a step here and get my u replaced. Okay, let's try example 8. First thing we always ask ourselves, can I expand my way through? Again, order of operations prevents us from distributing through. We're having to consider u substitution again. So this seems strange because if our u value is 2 minus x, this is definitely not higher than this degree, but we can still move forward. We can use change a variable to eventually get that x to be replaced, but we always want to target our u value to be what's inside the parentheses. Even though that's the higher degree, this is still the more complicated expression. So always look for your parentheses as our first option for your u value. Again, we're stuck. Two different variables multiplied together. We can't do power rule until that x goes away. So our pathway to get that x replaced is the assignments that we gave u and x at the beginning. So this is our pathway to get that x in terms of the variable that we want. So if I solve for x equals what? Two minus u, right? If I solve for x, if I move that x over to the left side, subtract the u over to the right, x equals 2 minus u. So there is our replacement. But there's still quite a bit of algebraic steps ahead of us. Even though we do have a pathway to our answer, we still need to do quite a few steps of cleanup. So we can't do power rule until we have to FOIL this out. We got to distribute that u to the 1/2 through. And once every term is nicely separated, then we can apply power rule. Let me rearrange this into a form that that feels more familiar. I like to have my single term out in front, and I'm putting that negative along with it. And once I expand that 2 minus u squared, I can distribute that through, but just be careful. We got to FOIL this out. We can't just distribute that exponent through. So we're still in the cleanup stage here. 4 minus 4u. It's basically 2 minus u times 2 minus u. Okay, so 2 minus u times 2 minus u, that becomes 4 minus 2u plus u squared. I combine the middle term there to be minus 4u. So distribute the negative u to the 1/2 through. Now we can do power rule. Now all the parentheses are resolved. Every term is nicely separated. There's no variables multiplied together. These are all separated. So now we can apply power rule. Add 1 to the exponent divided by the new exponent. 1/2 becomes 3/2 over 3/2. 3/2 becomes 5/2 over 5/2. 5/2 becomes 7/2 over 7/2. And then flip all the fractions and then bring back your u variable. Sorry, bring back your x variable. So we get 3/2 over 3/2, 5/2 over 5/2, 7/2 over 7/2. Flip all the fractions up. And don't forget, your answer will always be in terms of the original variable, not in terms of u. Your u variable is to allow our calculus process to be a little easier to follow. But then once we get to the end, we're done with the temporary variable. We want to bring back our original variable. Okay, the next thing that I want to show you is if there's bounds involved, you're just going to apply the problem like as if you don't see any bounds. And at the very end of the problem, you're just going to do a half bracket and then plug in the upper bound minus lower bound. So the bounds is the very last thing that you do, even though it's the first thing that you see. So just keep that in mind. Okay, so let's try page 41, example 1. Okay, does anybody still need this page? Okay. So example one, the first thing we do is look to see, can I expand? I mean, we could expand, but we talked about how anything greater than a degree 2, we should explore other options because you're not going to be expected to expand anything with a 3rd degree. So that's a good indication that this is going to be a use substitution problem. But even though you see the bounds from reading from left to right, we know that's the last thing that we do. So I'm just going to rewrite the problem without the bounds. So we know it has no impact at the beginning of the problem. Okay, so we're just going to treat this problem like we normally would. And let's go through our full process. This is going to be a full use substitution process. So we're basically going to get to the very end of the problem, and then the bounds will play a role at the very end. Okay, all right, so try that, and then I'll work through at the same time you do. Okay, so after use substitution, we're able to get to the point where all the x's cancel out, even the coefficients cancel out. So u to the 3rd becomes u to the 4th over 4. Bring back our original variable. And then half brackets. Now the bounds can be involved. You know that if bounds are involved, you know that you're trying to get to a number and that number is area related. You're not going to have a plus c. Instead, you're going to just have a number. So plug in the upper bound first. Okay, so we get to the very end, we place the u back in terms of x, and then plug in our upper and lower bound, and we get 15 over 4. Okay, any questions with that? Okay, we're not going to do example 2, but what I want to do is I wanted to go through a different method of doing this. I think, well, first I showed you the method that I think most of us are going to feel comfortable with. This is going to be the one that is going to feel more straightforward. But I want to show you a different method here because sometimes AP exams can design a problem where they're forcing you to go through a different path. So I want to show you a different way from this stage here. Okay. So the first method is bringing everything in terms of x, and then because your antiderivative is in terms of x and your bounds in terms of x, you got a perfect match. So you can plug in your upper and lower bound and get to the answer. The other way is you keep your antiderivative in terms of u, and then you adjust your bounds in terms of u, and you do everything in terms of u. That's the other option. So I want to show you that method. So this is evaluating in terms of u. So that means we have to convert the bounds. But what we don't want to do is we don't want to involve the 1 and 2 with the u to the 4th over 4, because then you're using x to plug in for u. Then there's a mismatch of variable. Okay. So the way you do that is you convert your x value in terms of u. And the way you do that is you use this conversion here. So in terms of u, that means if we start off with a lower bound of 1, x equals 1, then our u value would have to be x squared minus 2. Therefore, our new lower bound is going to be 1 minus 2, which is negative. And then if our original upper bound was x equals 2, then our u value is still x squared minus 2. But now it'll be u is equal to 4 minus 2, which is 2. So we go u to the 4th over 4, and then our original lower bound was 1. Our new lower bound is negative 1. Our new upper bound is 2. It looks like it didn't change, but now everything's in terms of u. Your antiderivatives in terms of u, your bounds is also adjusted in terms of the variable u. And now we can plug in. So we get 2 to the 4th over 4 minus negative 1 to the 4th over 4. We still get the same answer. So given the choice, I think most of us would prefer just getting everything in terms of x and then evaluating that way. But sometimes on multiple choice questions, they may throw out a problem that is in this form. So just be aware that there's another option to evaluate use substitution if everything's in terms of u, but you're doing your conversion of bounds before you plug in your expression. Even though I think this is the way that is less, it doesn't. Yeah, this is probably not our first option, but the advantage of this option is that if you do most of the work in terms of the conversion, then plugging in is going to be a little bit easier, a little bit cleaner, because there's less calculations to plug in because you've done a lot of the calculations ahead of time. So this will feel a little cleaner because you're splitting up the calculations into multiple steps. But you know, if this true response, you're never going to be asked to do it this way. You can choose this way if you want, but sometimes multiple choice questions sets up a problem in this form. So we just need to be aware of this form as well. All right, let's go to page 42. Let's talk about even and odd functions. We're going to skip the review at the top here. So even and odd functions, middle of page 42. An even function is where two sides of, you're going to have mirror images on both sides of your y-axis. So for instance, if I have a graph that is even function, that means between 2 points that are the same distance from the origin, you're going to have two equal portions. So the rule says that if I can just find the area of the region to the right of the y-axis, I can double it, and that will get me the full area on the other side. So if I have even functions, I'm always going to create duplicate mirror images on both sides of the y-axis. For an odd function is where you have equal but opposite. So if I have a portion that is above the x-axis, then I'm going to have an equal portion that's going to show up if I'm the same distance away. So if this is 2, this will be 2. If this is positive 2, this will be negative 2. Right. So even function, you're going to create mirror image on both sides of the y-axis. Odd function, you're going to create equal but opposite on both sides of the y-axis. All right, so let's look at example 3 here. Suppose g of x is an even function, and we have two regions provided for us. The region from 0 to 3 is a positive 2. The region from -4 to -3 is a positive 4. Find the region from -4 to 3. So I want to kind of create a step process for us to follow that will be able to handle all the variations of problems. So I'm going to have us follow these 3 steps. So the first is you're going to build your shorter interval first. Not your smaller area, just your shorter interval. So you're going to look at your bounds and pick out the shorter of the 2 bounds and build that. Okay. Once you build that shorter interval, you're going to fill out the other side of the y-axis. And then the third will be you're going to then graph your larger interval or fill in your larger interval. And I think this will allow us, especially if there's overlaps involved, we're going to have an easier time seeing where the pieces fit if we follow this form. So 1 and 2 is going to help you build that foundation, and then you can fill in the gaps if there's any overlaps involved. Okay. So let's look at example 3 here. Suppose g of x is an even function, and we have interval from 0 to 3 is 2, and interval from -4 to -3 equals 4. Okay, which one is the shorter interval here? Yeah, -4 to -3, right? So we're going to, even though that's a larger area, we're looking for the short interval. So this is going to be the first thing that you want to grab. All right, so let's do that. So I'm just going to create an interval from -4 to -3. And then I'm just going to call that region 4, positive things. Now it's an even function, so we've built the shorter interval. We're going to go ahead and fill out the other side. If this is a positive 4, what can we say about the other side? Also positive 4, same distance away from 3 to 4, so we know that this is going to be true. So we built the shorter interval, and we fill out the other side. Now we're going to graph the larger interval. At the beginning, it doesn't really matter because there's no overlap, so it doesn't feel like this is doing anything that we can't do if we just did it at the beginning. But I think this is a good it's a good foundation for us to handle more difficult problems later on. So now let's fill this in here. Now let's fill in 0 to 3, the gap. 0 to 3 shows an area of 2, positive 2. And if that's positive 2, then this side is also what? Also positive 2. So now we have everything filled out. We're not always going to add all these numbers together. We're just going to add up the numbers that they're asking for. So they just want us to find the area or the displacement from -4 to 3. So from -4 to 3, what is that going to add up to be? 8. So okay. All right, let's look at example 4. Same example 3, but now it's an odd function. So whatever we create on one side, we're going to create an equal but opposite. Again, you're going to start with your shorter interval and build that. Okay, but now it's an odd function. So before we look at the larger interval, we want the other side to show up. So what can we say about the other side? -4, yeah. All right, let's fill in the gap. 0 to 3 is 2. What can we say about this side? -2. It's an odd function, so we're creating equal but opposite on both sides of the y-axis. And now we're just adding up the portion that they're asking us to add up. the region from -4 to 3. What's that going to add up to be? 4. All right, so example 5 is really where this process is going to really help us going the order that I want us to. Shorter interval, fill out the other side, and then deal with a larger interval. So we're back to even function. Interval from 3 to 6 is 7. The interval from -6 to 3 is 12. Find the interval from 0 to 6. So between these two, which one do we want to start with? Yeah, 3 to 6. That's a shorter interval. So we don't care about the area. We care about the interval. We want the shorter interval, not necessarily the smaller area. So let's start with that, 3 to 6. Even function. So what do you know about the other side? Same. Now, I want to talk about something here. These are set in stone, okay? We are not going to add anything to these regions. These are already established to be 7 and 7. We're not going to overlap this with anything, okay? Now, the region from -6 to 3 is 12. So that's really talking about this whole thing, right? But we don't want to overstep on this, because if we create a huge dome from -6 to 3, that means we're adding to the area of 7. We don't want to do that. So let's just do this. Let's just say that, okay, this region from -6 to 3, it needs to add up to be 12. So the 7 is already set in stone. We're not going to step on this region, but we know that everything added up must be equal to 12. So there's 7 here already. What's the remaining portion? 5. And how do you split 5 up? 2.5 and 2.5. Okay. What some students want to do is they see that 12 and they want to do this. They want to say, oh, this whole thing is 12. But then you're creating a region above 7, and then this gets confusing, and then you're undoing that process there, and this is not really 7 anymore. This is 7 plus something else. So just remember that if there's any overlap, indicate that overlap in a separate region, and just understand that, okay, I already have something that's established. I just need to fill out the missing empty parts that's going to add up to the total area that I want. Okay, so now that I have that filled out, I'm just going to add up my region from 0 to 6, and that's going to total to be what? Yeah. Okay, we have one more section to cover for this unit, but we'll do that Monday after break, okay? And then after Monday, after we get through this lesson on Monday, we can start putting things together, and we'll start doing review for our test. I don't know when the test will be, but it won't be the week that we come back from break. Okay, no homework.
Bro, that's literally gonna happen.